Good afternoon, everybody. Welcome to Stat 201. This is week 4. We did not meet last week. It was Columbus Day. I trust everybody had a good time, though. Anybody do anything fun on Columbus Day? No? Homework? Catch up? What's going on? I need to know what's going on in the lives of college students. Otherwise, I get older. I lose touch with reality. Nobody did anything that they want to do. Can you even remember back that far? A week ago? Well, I cut down some trees with my chainsaw. That was kind of fun. And then I think I went kayaking too, but I don't remember for sure about the kayaking part. So, what are we doing today? We're going to talk about some of the stuff from chapter 5. There's a few topics that I want to make sure you guys understand. And then you will have the opportunity to ask questions about the homework. Homework number 3, which is due on, well, the syllabus says it's due on Thursday, but it was brought to my attention that it's actually in Blackboard, shows it's due on the 19th, which is Friday, if I'm not mistaken. So, I'm not going to change that. You can go ahead and have till Friday without a late penalty. However, I'm not going to change the due date for the quiz. So both the homework and the quiz are due on the 19th. And whatever the schedule here, it looks like they're due on, the homeworks are due on Fridays throughout. So there's an extra 1% I just gave you on your homework if you want to turn it in later. But I will answer questions on homework 3. So if you have any of those, be prepared to ask those as we move a little bit further into class. So, why is this thing saying that? Okay, so let's talk about probability then. What is probability? It's the study of uncertainty. Study of uncertainty. What do we mean by uncertainty? Randomness. That's one of the definitions, or rather, those things are really synonymous with each other. Uncertainty, random. What does that mean? That means that I don't know in advance what the outcome of an experiment is going to be. Okay, so is that something that I need to worry about? Yes, it is. Imagine this scenario. You get an email, and the email says, later this week, Apple stock is going to go up. And it gives some pre-specified day and time. And so I check, just for fun, on that day and time, and sure enough, what has the Apple stock done? Gone up. Okay? So what are the chances that whoever sent me that email was just guessing? It's either going to go up or it's going to go down, right? You might say it's going to stay the same, but we'll just say it's either up or down. So the probability of that happening is 1/2. Okay, so you say, oh, no big deal. The next week, what happens? You get another email from the same people, and this one says, Apple's going down. Okay? So, what's the probability of that happening? Well, the probability that they got it right, if they were just guessing, probability that they would guess right the second week is also 1/2. But if I look at it that, hey, last week they got it right, and then now this week they got it right, cumulatively, if I look at the joint probability, I would say probability of both being right is 1/4. Right? Pretty simple here. You're with me? Everyone's with me on this? Okay, what do you think is going to happen next week? The next week? I get a third email, and what does this one say? This Microsoft is going up. And sure enough, what happens? I check the specified date and time. Microsoft has gone up. So what's the probability that all three of those things happen? 1/8. Still, could be chance, right? Could be these guys just getting lucky and guessing. Well, let's say this happens for 10 weeks in a row. And finally, in the 10th week, they say that Amazon stock's going down, and the probability of all 10 things happening according to how they were predicted by these people is what? 1 divided by 2 to the 10th power. Now, do you guys know what 2 to the 10 is? What about, what is it?
That's the translate stock function.
I'm sorry, say again?
It's actually translate whether the stock function or not.
So 1/2 to the 10, that's the probability that they guessed all of these things right, if they were guessing. Right, they said Apple stock went up, and then it went down, and the Microsoft went up, and every week for 10 weeks I got different emails saying different stocks were going up or down. And so the probability that they get all 10 of those right is 1 divided by 2 to the 10, which is 1/1024. So about 1 in 1,000. Okay, so what are these guys doing here? What are they trying to do? What do you think is going to come in the email that I get in week 11? What's going to happen in week 11? Are they going to tell me this stock is going to go up or down? No, they're going to write me a really nice email that says, hey, over the last 10 weeks, we've accurately predicted rise and fall of these stocks. They give you a summary, and they say, we're just randomly guessing. Chances of doing that are about 1 in 1,000. Pretty unlikely. We're pretty good at predicting what's going on with stocks. So if you're looking for somewhere to put your money, you've got a whole assortment of instruments that you can invest in. And in fact, if you just give us your money, we'll take care of it all for you. And you just sit back and let us do our stuff, and you get the return. What do you guys think about that? It sounds pretty good, doesn't it? Is that what the stock market's all about? You find somewhere to invest your money, and okay, but what is it about this particular thing that should cause you to be weary? In other words, the right thing to do here is to take your money and run. Why is that?
They could send a bunch of emails saying that's going on, that's saying it's come down.
Okay, so that's exactly what they've done. They've said in the first week, they sent out, say, 1 million emails. And half of them say Apple's going up, the other half say Apple's going down. And then they wait and see what happens. It goes up, okay. Now we're going to send out 500,000 emails. Everybody who said Apple was going up to, and we're going to say Apple's going up to half of those, and Apple's going down to the other half. And then after week 2 happens, and Apple goes down, then we have a perfect track record with how many emails? 125,000. We're going to split those in half. We're going to keep doing that. So in week 10, how many emails am I sending out saying Amazon is going down? Well, it should be about 1,000, isn't it? At some point we get to about 1,000, and we're going to say, look, there's 1,000 people out there who think that we know what's going on. Let's get, we can even get a small fraction of those, small improper fraction of those, proper fraction, bigger than one. Small proper fraction of those people to give us their money, then we can go off to Cayman Islands and they'll never hear from us again. And have a lot of money and not have to earn it. So what's going on here? What are these guys trying to do? Well, let me bring up another web page. If you come over to, what's going on here? Is the internet not working for anybody else? Okay, in the week 3 folder, you will see a link that says ESP experiment. So we're going to do this experiment. And this is an experiment, an ongoing experiment by Clifford Pickover. And he's written a whole bunch of books on lots of different topics. And he is experimenting about ESP. So what is ESP? Extrasensory perception. Is that what that stands for? What does that mean? It means you can communicate with people non-verbally, just through like the field. You guys ever heard of the field? Maybe that's science fiction. I don't know. But he's testing this. So the way this works is he says, okay, there's 6 cards here. Everybody select a card. Now, his instructions are to say the name of it out loud, but I'm going to ask you to do that inside your head. But the idea is you want to make sure that you know which of those is your card. So just stare at your card and really concentrate on it. Okay, does everybody know what card they have picked out? Anybody not know what card they've chosen? Okay. Now watch what Clifford's going to do. And this is absolutely amazing. I'm going to click on one of these eyes here. It doesn't matter which one you click on. He removed your card, didn't he? Is your card up there? ESP, somehow, he's able to read your mind from, I don't know where he lives. But isn't that fascinating? How's he able to do that? Oh, all the cards change. Okay, so it's not that slick. But if you were doing this on your own, maybe you wouldn't notice that. Why? Because you're focusing in on one particular card. The colors don't really see which ones are red and black. So what's going on here? Well, I'm going to show you a video that will help you better understand, hopefully, what's going on. So let me turn the sound on.
We all lose the people that are important in our lives, and that's okay because today we are graduating. But someday we won't be here. Someday we are all going to die, especially your girlfriends.
Hey, Doghouse, one.
Okay, so what does that have to do with ESP and the stock price predictions, so forth? I mean, it was funny, right?
That you can't predict the future, and so yeah, it was great that Amazon and Apple stock went up, but nobody. It would have been very hard to know that in the 90s.
It would have been impossible to know.
Yeah.
In other words, Cliff Pickover is trying to trick you into, do this experiment, and you're like, whoa, my card's gone, you knew which one was mine. Better yet, you do it to the whole class all at once, where I get these emails where people are saying, this is what's going to happen, and then that's what happens. Those are all violations of randomness, uncertainty. The only way to know for certain what's going on, what's going to happen in the future, is time travel. That's the only way. If somebody comes to you and says, this is absolutely 100% what's going to happen, if it's a random thing they're trying to predict, then they're lying to you. They're trying to open your eyes and take your money and so forth. Okay, so that's kind of interesting, isn't it? You're going to remember that forever now. You got to be Superman to be able to do that. Fly faster than the speed of light. Okay, what about powers of two? Do you guys know what all these things are? We already said what 2 to the 10 was. What's 2 to the 6? Anybody know off the top of their head? These need to be committed to memory. So when someone says 2 to the 6, you say 64. When someone says 2 to the 4, you know that's 16. 32 for that one. Why is this important? Because the human brain doesn't really think about exponential things very well. We're very good at thinking about linear growth, and when it comes to multiplying things together and getting very big very quickly, that's something we actually have to work at. Now, I have a brother who works at, I forget where he works now, but he lives in Washington, D.C. area, and he has top secret security clearance, and so he does a lot of projects where he's using that security clearance. And so on his resume, he puts things like worked for the United States Air Force doing stuff, and consulting doing stuff, and then the next line worked for some other company, KPMG, doing stuff. And so his resume is out there in cyberspace, and this was a few years ago. Someone at Google saw his resume and he said, hey, that's interesting. Stuff is interesting. Why don't we call up this guy and interview him and see if we want to give him the job offer and make him move to California or whatever. And so they called him up and said, hey, we saw your resume. We thought that was real cool. And you do stuff. And they said, what type of stuff do you do? And he said, I can't tell you. And anyway, so they asked him a bunch of questions. But one of the questions they asked him, and this was back when Google tried to, they say they used to try and hire the top 20th percentile of IQ, and so they had a bunch of these tests or questions they would ask, and they said, look, if you're stranded on a desert island and you need to know what the value of 2 to the 24 is, and you don't have a computer, and even though you're stranded on a desert island, you don't have all the time in the world, because if you can get a close approximation to this number, doesn't have to be exact, but pretty close, if you can do that in, say, 10 or 15 seconds, then you can get off the island. And if you can't, then you're going to be stuck there forever. So they asked that question. So what would you guys do? How would you approximate this quickly? Any ideas? Well, you would have first of all, hang on a second, you would have first of all paid attention to your stat professor and memorized all of those numbers so that you know that 2 to the 10 is 1024, and you know that 2 to the 6 is 64, and 2 to the 4 is 16, and so forth. Now, someone raise their hand.
I was just gonna say add it up.
So you could add it up, but could you get to, could you do that? If you kept doubling it in 15 seconds, could you get there? Probably would take you long. Okay, that's good. I like that. What were you going to say?
I was just going to say that you do 2 to the 10 times 2 to the 10 times 2 to the 4.
Okay, so we'll write that out. We have 2 to the 4. We know that's 16 times 2 to the 10 times 2 to the 10. So this is approximately 16. 2 to the 10 is about 1,000. It's 1024, but it's pretty close to 1,000. So I'm just going to put 3 zeros in here and 3 zeros in here. So 2 to the 24 is about 16 million, which is kind of interesting, isn't it? That you can do that. In fact, you could say, what's 2 to the 63? How long would it take you to figure that out? Well, this is 2 to the 3rd times 2 to the 10 times 2 to the 10. 2 to the 10. How many times? So this is approximately 8. Times 10 to the 18. Eight times 10 to the 18. So that's useful. And I don't know if that'll help you with an interview at Google, because I think they've changed their criteria because they had just a bunch of nerds working there and they wanted to change that, I guess. I don't know. But that's interesting, isn't it? No one finds that interesting. You find that interesting. Okay, good. I'm glad. All right. So, questions, comments about any of that so far? So counting is an interesting thing. And there's one rule that is the basis for all of the counting methods that we'll talk about in this course, and that's called the multiplication rule. And what does the multiplication rule do? Well, we already kind of talked about it. It says if we have a process that has sub-processes, and I want to know the number of ways in which I can complete the process, all I have to do is count the number of ways I can complete each sub-process and multiply those together. So the first email that came out, how many different emails are there that could be sent? Well, there's 2. Apple goes up, Apple goes down. Okay, for the second email, now how many different emails are there that could be sent? 2. Microsoft goes up, Microsoft goes down. All right, so we said there's 4 different ways in which we could have Apple go up and down in 1 week, and then Microsoft go up and down the next week. And that's where we got this 1 out of 4 probability. All right, there's 4 ways that can happen. Only one of those is going to happen. So 1 divided by 4, and so forth. So after 10 weeks, we've got that 10 times, so we get 2 raised to the 10th power. Okay, so other applications of this include something that I think is pretty interesting, and so I'm going to ask you guys a question. What's the probability of all of the people in this room, what's the probability that at least 2 of us have the same birthday? Okay, now I don't want you to necessarily look this up. What I want you to do is just tell me what you think this is without calculating it. Again, if you were on a desert island or something like that, what's the probability at least 2 people in the room have the same birthday? And this is day and month, not the same year. So there's, and imagine that there's no, we're not going to take into account leap year. So there's 365 different days people can be born on. And there's probably 40, let's say there's 40 people in the room. So of the 40 people in the room, what do you think the probability is at least 2 of us have the same birthday? And again, this shouldn't take you too long because, you know, just flying by the seat of your pants. We've got 20 results so far. There's 43 of you guys out there. So if you haven't gotten your answer in, please do so. Okay, anybody still working on that? Not that they want to, All right, let's look at these results. What's going on with the internet? Anybody else having trouble with the internet? Is this working? try this again. Okay, so here we have, someone says about 9%. We have 0.000, how many zeros is that? 5 zeros and then a 3. So that's a really small number. 4 zeros and then a 7, 3 zeros and then 2 7. Finally, we got to 2%, 2.5%, 5%, 1%, 11%, 12%, 14, and 25%, 30%, 60, 70, 80, 90%, 80%, 70%. So there's a few on the 900,000 to 1. So we have one person saying almost certainly it's going to happen, and we have 90%, 2 people saying 90%, or 1 person 90%, a couple of 80%, and then everybody else is saying numbers that are very small. So you should be willing to take the bet that I'm going to offer you. I think if we have 44 people in the room, which we do, if we have 44 people, I think there's a high probability that at least 2 of us are going to have the same birthday. That's day and month, not the year necessarily. And so if you disagree with that, you have the opportunity to bet me. And if you win, in other words, if you take the bet and there's no one in this room that has the same birthday as anybody else in the room, then you don't have to come to class anymore. You don't have to take any quizzes, homeworks, exams, anything like that, and you get an A in the class. That's if you win the bet. If I win the bet, almost exactly the same thing happens. You don't have to come to class anymore, no quizzes, homeworks, exams, nothing like that. But instead of an A, you get an F. So, whoever said that number right there should be probably willing to take me up on this offer. Whoever it was, do you want to? No? Anybody else want to? I mean, this is an opportunity for you to save countless hours and aggravation over the next 6 weeks. You can write home and tell your parents, I already have an A in the class. No? No one's going to do it? Okay, well, before we actually calculate the probability, let's find out what your guys' birthday is. Okay, so before we shut this down with 33, I'm going to need all 44 people in this room, including myself, to submit an answer. And please put the format as first 3 letters and then the day. And this is an easy question. You all should know the answer to this one. So let's get those responses in as quick as possible. We got 36, 37, 7 more. Think really hard. If you don't know your birthday, text your parents. They'll remember. 41, we need 3 more. This is really important, actually. So we must have some technology issues or other issues. But let's look at this then and sort. So April 14, 16, 29, 9, August 27th, 8, 19. October 1st. Raise your hand if your birthday is October 1st. Oh my goodness, you guys are almost sitting next to each other. Are you kidding me? Is this rigged? Is this Cliff Pickover? No, it's not. Any other matches? September 28th, 29th, 19, 7. Okay, so there was just one pair. Thank you very much. You guys made this work perfectly. When I did this morning, I had 3 different pairs of students that had the same birthday. So what's going on here? Is that astounding to anybody? And most of you said the probability was pretty low. I think it's pretty high. How do you calculate the probability of at least 2 people having the same birthday in a room? Well, what does that mean? That means you could have the 2 gentlemen that had the same birthday. You could have any other pair. You could have multiple pairs. You could have triples. You could have some triples, some pairs. You could have quadruples, triples, and it's even possible that everybody had the same birthday. Right? Pretty unlikely, but possible. So if I want to calculate the probability of that happening, the easiest way to do that is to use the law of complements that says, what's the probability of it not happening? And I'm going to subtract that from 1. So what's the probability that that no one shares a birthday? No shared B-days. Whatever that probability is, I'm going to subtract it from 1. And so let's just do that. We'll take 1 minus. If I have 44 people in the room, I'll first of all say, how many ways can the first person have a birthday such that nobody else has the same birthday? And you would say there's 365 different ways. Again, we're ignoring leap year, and we're assuming people are born randomly. Any given day of the year has the same chance. So there's 365 days the first person can be born. And if that's the case, what's the number of ways the second person can be born, or the number of days the second person can be born on? They can be born on any day except for the one the first person was born on. So 364, and then we have 363, 362, and so forth, all the way until we get down to 365 minus 44 plus 1. And in the denominator, we get the number of ways in which we can have 44 birthdays without any restrictions. So the first person can be born on 365 different days. The second person, 365, 365, 365, and so forth. And we have 44 of those things. So we get 1 minus the number of permutations of 365, taken 44 at a time, divided by 365 raised to the 44th power.
Why did you plus 1?
Because I wanted to, so if I have 44 of these, then the next one down here should be 365 minus 44. So the way permutations work, if we have permutations of n comma r, this is going to be n factorial divided by r factorial, divided by n minus r factorial. So I want this n minus r factorial to be that number right there. So if I've got 44 of those things, by the time I get down to this spot, what's left is whatever that is. 365 minus 44 is 321. So it should have three. Oops. So this is really 321 factorial divided by 321 factorial. That's so one way to think of this is if I take 365 days and I break it up into two groups, one has 44, the other has whatever's left over, and I want to say how many ways can I rearrange all those things. So try it out. Say we've got 4 people in the room. So 365 days the first person can be born, 364, 363, 362. And then I have 361 factorial, but I don't care about those. So this is 365 minus 4 plus 1. Does that make sense? Yeah. It's just makes it work out, right? For this problem, it's always plus 1. Yeah. Right, because I'm saying instead of, if I just have 4 people in the room, I want to know how many ways can 4 people have different birthdays that don't match. The first person can be born on 365 days, right? And then the next person, 364, 363, and then the fourth person can be born on 362 days. Right, so 362 is, it's just 365 minus the number of individuals that I have, so 4 in this case, but that's 361, isn't it?
Why would you just go down to 362?
Because I've got 4 people. So 1, 2, 3, 4 different people. I didn't want to write it all out 44 times. So I said, let's imagine we have 4 instead of 44. But it's the same thing. So this is 361, but that's not 361. So I've got to add 1. That's just the way it works out in this situation, this example. You can just you can write it as this, P of 365. So this would be 365 factorial divided by 365 minus 44 factorial. So that's 365 factorial over 321 factorial. Same thing here. If I have permutations of 365 taken 4 at a time, that just means I have 365 factorial divided by 361 factorial. So the 361, the stuff in the denominator, imagine I kept writing these out. And then I divided by that. The 361 factorial is where I start dividing. So come talk to me. We can work on that later. Okay, so in the numerator I've got a big number, but in the denominator I've got a really big number. And it turns out that the probability here is about 0.9326, I believe. There's about a 93% chance that in a group of 44 people, at least 2 people are going to have the same birthday, which is pretty big, isn't it? I think it's pretty big. If you come over here to the week 3 folder, you can see there's a birthday problem generator. If you click on that, there's this nice applet that says, let's drag this up to 44. This is made by the people in LeBeau Tech. And click show probability, 93.28. I said 93.26. That should be an 8. So what does that mean? That means if I randomly select 44 people, then there's a 93.28% chance that at least 2 will have the same birthday. And I can have this program do that for me just by clicking X1 sample, and I can do that another time. And in this one I see there's a bunch of matches. If I do this over and over and over again, this little box over here is keeping track of how many times I have the result come out positive. So if I want to do it 5,000 times all at once, just click on that, and it says 93.39%. That's pretty close to what it should be. And if I do it again and again and again and again, eventually that will converge to the 93.28, although it doesn't look like it's moving there right now. So if I have 50 people in the room, what do you think the probability is? 97%. If I have 65 or 60, let's put it up to 60. 60 people, it's over 99%. So what value do we have to have in order for it to be 50%? What do you think? It's obviously going to be less than 44. Yeah, it is. How about 25? Let's try 25. 25 is 56%. 24 is 53%. 23 is 50.72%. So if you have 23 people in a room, imagine you're at a party on Friday night with all your friends, and you need to scrounge up some money to pay for the pizza. What are you going to do? You're going to start taking bets. Okay, guys, what do you want to bet? We've got 30 people in the room, 50 people in the room. Most people think the probability of having more than one person with the same birthday, more than 2 people with the same birthday, is pretty low. So you should be able to get some takers. Yeah? And then you pay for the pizza, which is good. Okay, so you can get on and play around with this if you like. It's kind of an interesting problem that, for some reason, people get they show a lot of attention towards this. When people have the same birthday, they get excited, and it turns out that it's not all that uncommon to have people sharing birthdays. So. Let me just say one more thing about this, and we'll take a break. Intuitively, what's going on here? A question?
You know, within that data set, how many duplicate birthdays are there?
What do you mean?
Like, if you looked at all 1,000 birthdays, how many of them are duplicates?
You mean this particular?
Yeah, in that particular data set.
This data set right here? So there's 3.
Okay.
They're matched up in yellow. But that's just one sample. If I click sample again, I'm going to get, so this one has 23. Well, that one had what, 44, 80. Yeah, so this applet will highlight all the duplicates.
Okay.
But you might say, so there's going to be 80, in this case, 80 birthdays. If we had 44 people, as we do in this room, why do you think that number's so high? What drives this? So think about the number of pairs that we have with 44 people. So we're not even talking about triples or quadruples or 5 people with the same birthday. We're just talking just about the pairs. Pairs of people with the same birthday. How many pairs are there? I have 44 people. This is the same thing as if, the way to think about this is if we all went to a party and we shook, everybody met everybody at the party, so everybody shook everybody else's hand. So how many handshakes are there? How many unique handshakes are there, I should say? Well, the first person is going to shake hands with how many people? With 43 people. And then the second person is going to shake hands with how many people? 42, 41. Really, they're shaking hands with 43, but we already counted that handshake in the first person's total. And then finally, we're going to have 3 plus 2 plus the last person. The last person, how many are they going to shake? 0. You can't shake your own hand, let's say. Okay, so we'll just leave the 0 off. But if I add all those numbers up, what do I get? Do you guys know who Gauss is? You heard of Gauss? The mathematician from Germany who was really smart even as a kid, and when he was in grade school he would get into trouble because he was, now he would be labeled as being ADD or ADHD or whatever, but he was just so bored because everything was too simple for him that he got into a lot of trouble. And the story goes that one day he was doing something and got in trouble from the teacher, and the teacher said, "You have to stay in during recess." And so all the kids left except for him, and his punishment was that he had to add up the numbers from 1 to 1,000. I don't know, 1 to 100, 1 to 1,000, something like that. And the teacher said, when you're done with that, and you thought long and hard about what you did, then you can go outside and play with the other kids. And if you don't get it done this recess, don't worry, because there's plenty more recesses. We'll finish working on it throughout the weeks, if it takes you that long. And so, what did he do? He said, "Okay, you got me." He went and sat down. He's 9 years old or something like that. Sat down at his desk, scribbled on his slate for about 20 seconds or so, and then walked up to the teacher and handed him the slate, said 5,050, and went outside to play. And that was the total sum of the numbers from 1 up to 100. And so how did he do that? What did he do? He said, let's take the first number and the last number and add those together. When you do that, what do you get? 44. And then he said, let's take the second number and the second to last number and add those together. What do you get? 44. Third and third to last. Add those together, and you get 44. And he's going to do that until what happens? Until he gets down to the middle, and he gets 22 right there in the middle all by itself. And so this is going to be equal to, and you sum all this up, you have 44. How many times do you have 44? 21, okay? Plus, you got an extra 22. Okay, so this is going to be equal to 44 times 43 divided by 2. And in fact, the general formula for this is n times n minus 1 divided by 2. If I'm adding up the numbers 1 to n, it's just n times n minus 1 over 2. Sorry. N times n plus 1. Make sure we get that right. So if I'm adding up the numbers from 1 to 43, that's the number of pairs that I have out of 44 people. So if I'm saying how many pairs are there out of 44 people, it's n times n minus 1 over 2. All right, so it depends on which of these formulas I use, n times n minus 1 or n times n minus n plus 1 over 2. Whichever one I'm going to use depends on what it is I'm specifying as my n. And this is just combinations. If I have n objects and I'm choosing 2 of those, that's going to be n factorial divided by 2 factorial divided by n minus 2 factorial. And that's just n times n minus 1 divided by 2. So if I have 44 pairs, 44 individuals, how many pairs do I have? I have 22 times 43, whatever that turns out to be. Is that a lot? Yeah, that's a lot. I mean, so let's pull that up. Let's just put that in here, 22 times 43. That's 946 pairs. Okay, so if I want to know the number of triples that I have, how would I do that? It's just going to be 44 choose 3. That's the number of triples. And the number of quadruples, 44 choose 4, and so forth. Now, that doesn't tell the whole story because just because we have 946 pairs that could have the same birthday, there's lots of different ways in which we can have or not have each of those pairs have birthdays. But this is, at least intuitively, one of the reasons why that probability is so high, because there's just so darn many pairs of people, and we have 44 people. Okay, so let's take a break. Everyone's so talkative today. All right, so I want to look at one more example of a probability topic, and that is something called Bayes' theorem. And Bayes' theorem is the basis for updating probabilities of events of interest, and actually forms the basis for a whole branch of statistics that is a little bit different than what we're learning in this class, called Bayesian statistics. But if we have the probability of some event A taking place conditional on some other event B, then we can write that as the probability of B conditional on A times what's called the prior probability of A, or the unconditional probability of A, or we can also call that the marginal probability of A, divided by probability of B. So here we start with the prior probability on the right-hand side. We say, okay, if B happens, that's additional information. We want to use that information in order to update the probability that A is going to happen. So we get the posterior probability on the left-hand side. of A. So probability of A given that B has happened. That should be different than the probability of A if the events A and B are not independent. So if they're dependent, those things will be different than each other. So here's an example of where Bayesian, or the Bayes theorem, can be used to illustrate how information can make us better off, or at least help us to update the probability of success. And there's a game called Let's Make a Deal that came out back in the 70s, and it was pretty popular for a long time. And at the end of the game, this was like a game show on TV. At the end of the game show, oftentimes, whichever contestant had kind of, won their way up to the top, they were brought before 3 doors, and they were told behind one of these doors is a fabulous prize. Behind the other 2 doors are donkeys, or some gag gift or prize that you don't really get to take home. And unless you live in Lancaster County, you probably don't want to take the donkey home anyway. But so the way it would work is the person would pick a door. So who wants to play this game? All right, pick a door. Okay, you pick door number 2. And then the game show host, Monty Hall, would say, okay, he picked door number 2. Let's open up door number 1 and show you what's behind door number 1. And what's that? It's not a fabulous prize. It's a donkey. Okay, so at this point, you can either stick with your initial pick, door number 2, or if you like, you can switch to door number 3. And so I want to ask you guys what you think is the best strategy for doing this. And so let me pull up this next question. So again, you can either stay with your initial pick, you can switch to the other pick that's still there, or you can say it doesn't matter, in which case then you have to decide what it is you want to do. Alright, so let's look at the results and see what you guys are saying here. We've got 36% say to switch, about half of you are saying to stay, and 17% says it doesn't matter. So those of you that said it doesn't matter, does anyone care to say why you think it doesn't matter? I guess I'm not that surprised. I haven't gotten you guys to say anything else all day, so I'll venture an opinion and you can just shake your head or nod if I'm headed in the right direction. If you think that it doesn't matter, you're saying, well, there's 2 doors, and I know behind one of the doors is the prize, behind the other door is the donkey, so chances are 50-50 that I'm going to win, so I can pick either of those and still have 50-50 chance. Is that what you're thinking? Okay. Those of you that said to stay, maybe we're thinking something along those same lines, but then you're saying, in addition to that, first impressions tend to be good, maybe. If you switch away from winning, you're going to kick yourself. Does that explain it, what you're thinking? No? Yes? Any other opinions for why you would want to stay?
I want to say it's good.
Okay, what about for switching? Those of you that said to switch, why would you want to switch?
When you have 3 options, you have 1/3 chance and you pick from the 3 options. So once you deal with the second one, then the option to switch gives you 2/3 of the chance. If you do it enough times, the probability of switching and happening to you better closer to being 2/3 than it being 1/3 as it did in the original process.
So what you're saying is, instead of there being a 50% chance here and 50% chance here, you're saying if I switch, you're actually saying there's a 2/3 chance here and a 1/3 chance here. Is that what you're saying? Okay. What do you guys think about that? That's right. But why is that right? Why is it not 50-50?
Because the original option was 1/3, so that would be misinformation. So we have
So when you're exactly right. When you made your decision, the chance that there's money behind door number 2 was 1/3. Now you've gotten some information, but that information actually doesn't change the probability that the prize is behind door number 2. But it does tell you one door that it's not behind. And so think about it like this, what's the chance that you picked a donkey behind door, what's the chance there's a donkey behind door number 2? Well, that's going to be 2/3. Right, so if you switch and you picked a donkey initially, you're going to switch to the money. So what's the chance you picked a donkey initially? 2/3. What's the chance you picked the money initially? 1/3. So if you pick the money and you switch to the donkey. If you pick the donkey and you switch to the money. So the best thing to do is to switch. If you do that, you'll win 2/3 of the time. And so we can actually use Bayes' theorem to show that that's true. And I don't know if we want to get into that today or not. Which time we got? So let's do Bayes' theorem real quickly on this one. Okay, so Monty Hall opened up door number 1, right? So we're going to say M is the event that Monty Hall opens door number 1. And we're going to say $1 is the event that the money is behind, or the prize is behind door number 1. And the probability of that is the same as the probability that the money is behind door number 2. And that's the same as the probability that the money is behind door number 3. And that's all equal to 1/3. M is going to be the event that Monty Hall opens door number 1 and given that you pick door number 2. Right, that's the scenario we have here. You pick door number 2 and Monty Hall opened door number 1. So what do we want to know? We want to know what's the probability that the money is behind door number 2 given that Monty Hall opens door number 1 and you pick door number 2. And that's going to be equal to, according to Bayes' theorem, the probability that Monty Hall opens door number 1 given that the money's behind door number 2 times the prior probability that the money's behind door number 2. All of that divided by the probability that Monty Hall opens door number 1. And of course, that's still given that you pick door number 2. Okay, so this is just Bayes' theorem. The notation is a little bit different. Call A and B different things. But that's really what's going on. So how do we calculate this? Well, the first thing we need to do is find out what the probability of M is. What's the probability that Monty Hall opens door number 1? Well, that can happen in one of 3 different ways. we have the probability that he opens door number 1 given that the money's behind door number 1 times the prior probability that the money's behind door number 1. Or he can open door number 1 given the money's behind number 2 times the prior probability the money's behind number 2 plus the probability that he opens door number 1 given the money's behind door number 3 times the prior probability that the money's behind door number 3. Okay, so do we know what these things are? Well, the prior probabilities, $1 and 2 and 3, those are all equal to a third. And so now, given that the money's behind door number 1, what's the probability that he's going to open door number 1? Also keeping in mind the fact that you chose door number 2. Okay, so imagine that this is not a donkey yet. It's just door number 1. So you don't know what's behind there. But Monty Hall's never going to open a door and show you the prize. He's only going to open the door that has a donkey behind it. And if he has a choice, he's going to randomly choose between the donkeys to reveal. So, given that the money's behind door number 1, what's the probability he's going to open door number 1? 0, right? He's never going to open door number 1 to show you the money. He's only going to open a door with a donkey. Given the money's behind door number 2, the money's behind door number 2, you pick door number 2, so let's draw this back in. If the money's behind door number 2, what's the probability he's going to open door number 1? Should be a half, right? Because if the money's behind door number 2 and you pick door number 2, he has his choice. He's going to randomly select between door 1 and door 3. So this is going to be a half plus, given the money's behind door number 3, what's the probability he's going to open door number 1? You pick door number 2, so he can't open that one. But if the money's behind door 3, that means he has to open door number 1. So multiply all those together, and we get 1/6 plus 1/3, which is a half. So that's the denominator up here. So what do we get for the numerator? The numerator is just this part right here. So a half times a third, which is a third. So the probability that the money's behind door number 2, given that he opened door number 1, and that you picked door number 2, is a third. So if you switch, are you going to win? Well, maybe. But what the appropriate question is, what's the probability you're going to switch if you win? And it's 2/3. Probability you're going to win if you stay is 1/3. So we just wrote that out. In other words, what's the probability that the money's behind door number 3, given that he opened door number 1? That's going to be the probability that the money's behind door number, or that he opens door number 1, given that it's behind door number 3 times the prior probability of 3, all of that divided by the probability that he opens door number 1. So we have exactly the same thing, 1/2 in the denominator. But in the numerator now we have 1/3, which is, when we divide a third by a half, we get 2/3. Okay, so that's pretty interesting, isn't it? Well, the interesting thing, one of the interesting things about this is, if you think that it doesn't matter, then you should randomly choose between the 2 doors that are left, right? I mean, if that's really what you think. If you think the probability is 50-50 at this point, well, guess what? You're right. if you think that. In other words, if I randomly select between staying and switching, what's the probability I'm going to win? It's a half. Why? Because if you average 1/3 and 2/3, you get a half. So half the time I'm going to stay, half the time I'm going to switch. If I average those probabilities of winning 1/3 and 2/3, then I win half the time. So if you think about it like this, you say, oh, it's a half. It doesn't matter what I do. You're kind of shooting yourself in the foot, because the probability that you win could be 2/3 if you switch. But if you randomly choose between switching and staying, then you're kind of keeping yourself at that level of at 1/2 probability of winning. Okay, so questions about that? Thoughts, comments? Everyone's good? It's kind of interesting though. Okay, so homework number 3, chapter 5. Are there any questions you guys have from this? No? None? Okay, well, if you don't have questions, I'm not going to manufacture answers just for the sake of doing that. So I'll tell you what I'm going to do. I'm just going to sit right here until one of two things happens. The clock says 1:50 or all you guys leave. And with that, we're done with class unless you have questions. Come down and see me.